one side times the sine of the angle on that side is equal to the index on the other side times the sine of the angle on the other side. And so if you go to a bigger index, the angle gets smaller. If you go to a smaller index, the angle gets bigger. This product has to remain constant. If you're going from the bigger index to the smaller index, you can have in a critical angle get bigger than the critical angle. You have a total internal reflection going on, and the sine of the critical angle, which is when the theta 2 is equal to 90. So you're going from a bigger index for theta 1, smaller index for theta 2. Sine of the critical angle then would be the N2 over the N1, because sine of 90 is just 1. But remember, N2 has to be less than N1 in order to have that angle. So like seeing the fish under the water. Light coming from the water into the air. Going from 1.33 to 1. And so you've got a critical angle there, which means fish is in the wrong place. You can't see it even if the water is perfectly clear. Because the light is from the fish to the surface, is hitting the surface at an angle bigger than the critical angle, and therefore nothing is coming out to you anyway. Not at some other angles, because light's coming out from the fish in all directions. Some other angles would be going into the air, but if you're in the wrong place, you can't see the fish. So for the total internal reflection, this is your critical angle there. And that was with Snell's law. For mirrors and lenses, we've got an object in front of the mirror of the lens, starts out in front. Where does the image end up? And what's the focal length of this mirror or lens? And so the 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. That's our equation for both mirrors and lenses. And then the magnification is the minus the Q over the P, or the size of the image over the size of the object. Think in terms of just how big is the image compared to how big is the object. That's the magnification. Magnification bigger than 1 says the image is bigger than the object. Magnification less than 1 says it's smaller than the object. If it's equal to 1, they're the same size. If the magnification is negative, it means the image is upside down compared to the object, going in the opposite direction. If it's positive, it means the image and the object are both pointing in the same direction, either both up, both down, whichever way. And then you've got the focal length is 1/2 of that, whatever the radius of curvature of the surface is. As far as sign conventions, for mirrors, positive on the front side, negative on the back side. And that's true for image or object or focal length. So if it's concave, then you've got the focal point is on the front side, so it's positive focal length. If it's convex, that means it's a negative focal length, because the radius would be on the back side, focal length on the back side. It's the convex, remember, it's curved toward you, concave is curved away from you. For the lenses, P is positive on the front, negative on the back, but Q is positive on the back side, negative on the front side. Light goes through the lens. Remember the positive Q, positive image, is a real image. The negative image is a virtual image. The real image can be projected onto a screen, and you can see the image on the screen. Virtual image, light goes on the screen, but you don't see an image on the screen. So, the difference there. And then for focal length, if it is it's positive, if it's a converging lens, and it's negative if it's a diverging lens. So, one thing to remember there, or be careful of there, the problems may not tell you that it's, say, negative. It may say this is just a convex mirror. It may say this is a diverging lens, and then just give you a number like 15 centimeters for the focal length. But if it says it's diverging mirror or lens, or says it's a convex mirror, if whatever you're given for the focal length, you've got to put it in as a negative number when you put it into the equation. It's, even if the number they give you in the problem is some positive number.
But if it's a negative number?
Well, if it says it's negative, then it's, it doesn't have to necessarily say it's divergent then, or convex. Don't change if it says it's negative, don't change that to a positive. You could say this is a convex mirror with a focal length of negative 20 centimeters. That's fine, it's negative 20. But if it just says this is a convex mirror with a focal length of 20 centimeters, it doesn't give you the negative on that number. Well, when you go to this equation, you still have to put that number in as a negative number, if it's either convex or divergent. Okay? So all your mirrors and lenses problems, you're going to be using these equations. If it's a double lens, you got two lenses, one right after the other. So here's one lens, here's a second lens, they're separated by some distance d. You've got some focal point for the two lenses, and they don't have to both be converging. They could be diverging. One could be converging, the other diverging. Whatever they are. Just two lenses separated by some distance. Start with some image for the first one, or object for the first one. You go through the equation once, find the image of the first one, and then the image of the first one becomes the object of the second one. So the P2 is the first image, Q1 is up there, then the P2 is the distance from this first image to the second lens. Then you look to see, well, is it on the front side or the back side of that second lens? Remember, as your way I'm going to draw them is left to right. So where the first object starts, that's the front side of the first lens. The other side is the back side. But then the second lens is always going to be on the back side of the first lens. So this is the front side of the second lens, and this is the back side of the second lens. So where is that first image? Is it on the front side or the back side of the second lens? How far is that first image from the second lens? What's the distance there? That gives you the P2, and then if it's on the front side, it's positive. If it's on the back side, it's negative. And so you go through that, the second lens, find where the final image is, which could be on this side, it could be in between, it could be back here somewhere. Just depends on what the numbers are at that point. But you go through that again, and if they're asking you for the total magnification, what's the final image compared to the original object, then the total magnification is the magnification of the individual magnifications for each lens. So it would be minus the Q1 over P1 times the minus Q2 over P2. whatever you end up with that. And that could be positive or negative, just depends what the P's and the Q's are. But that's if you're a double lens, and again, we're not gonna do anything with double mirrors, so if it's double something, it's always a double lens type problem. So that's all your mirrors and lenses stuff. We talked about just interference in general. We're not really gonna get into what involving interference in general. And specifically, we'll be doing diffraction. And so you have your two or more openings, a screen, distance L, the distance D between the openings, and it bends the light at some angle, and then on the screen from the m equals 0 point to say the m equals 1 is some value, call it y. Now, remember this goes both directions. You can have m equals 1, you can have an m equal 2, not further. And this depends on, you have multiple m's there depending on what the wavelengths are and what the d is. But your basic equations are that the d times the sine of the angle is going to equal the m number times the wavelength. This is for constructive interference. And we're not going to do it for destructive interference for these. And then your other one is the tangent of the angle is the y divided by the L. So how far from the central point are you? Y value. What's the distance between the openings in the screen that you've got? If it's a grating, you've got multiple openings, then that D is the reciprocal of the N, which is the number of openings per unit length. Like the one we used in the lab has 600 openings per millimeter, which gave us a D then of 1.6 for every 10 to the negative 4, or negative 3 millimeters, then that was 10 to the negative 6 meters. And it was just 1.6 for every 10 to the negative 6 in terms of meters. But in this equation, you have to put D in meters. So even if N is in millimeters or centimeters, when you get the D in those units, change the D into meters before you stick it into this equation, so your lambdas are in meters. Sort of the standard unit for that. Nanometer is 10 to the negative 9 meters. But we've got those equations. That would be with either two openings or a grating which has the multiple openings. We still use the same two equations. So we've got diffraction. Polarization. And the only one we've got there is polarization by reflection. So if you've got light in one medium and it refracts into a second medium, so you do a bigger one there, but it also reflects. And this angle should be the same as that angle because it's reflection. If the reflected and the refracted ray are 90 degrees, then this reflected ray is 100% polarized, and it's polarized parallel to the surface, electric field, parallel to the surface it's reflecting off of. Like the water reflecting off, less sunlight reflecting off parallel. And the appropriate angle there is the tangent of this angle, which is called the polarizing angle, is the N2 divided by the N1. Again, that comes from working Snell's law and making this angle 90. That's when it's 100% polarized. talking about polarization as far as numeric type problems, that's the only equation we've got for that. Trying to remember if there was anything else we had. Notes. Okay, refraction, Snell's law, critical angle. There is lenses, polarization by refraction, diffraction, ratings, resolution. And so if you've got a opening, this could be like the diameter of the telescope or the diameter of the pupil in your eye. And you've got 2 points over here that are emitting light, separated by some distance s, both the distance presumably r away from you. You've got some angle here, and the relationship there is the s equals r theta. But that minimum angle, in order to resolve these 2 points, so you can actually see them as 2 separate points, is equal to the 1.22 times the wavelength of light coming from these to your opening, divided by the diameter of the opening. So that's our resolution equation there. So that's the basic equations on everything. The only other thing I can remember would be like if something reflects off of a larger index material. So like if this is air and this is water, the light reflected here, you have to be polarized. But also the reflection at that point creates a half wavelength phase shift. And that's when we were talking about just interference in general, like you had the source of light, the ray goes this way, and here's your detector, it goes straight from the source to the detector. But so the light coming from there reflects off of something down here. And so you've got this path length, and you've got now this path length from here down to here to here. And so is this going to be constructive or destructive? Well, if this is either a bigger index into N1 into bigger than N1, or this material is a conducting material, like a piece of metal. Then on that reflection, you get the half wavelength phase shift, which then changes it from being just the path difference equal to the integer multiple of wavelength for constructive interference into the path difference plus the half wavelength phase shift has to equal then m lambda to get constructive interference, which would mean then the path difference has to be a half wavelength difference, one half or 1.5 or 2.5 or 3.5. Both of these cases, the m is the 0, 1, 2, ... So it's not just this, it's this if you got that phase shift going on. And that was one example of that. I know I did one example like that in class. Gave you a wavelength, gave you this distance, and this hits halfway, and so you calculate this distance, and so you get the difference in the 2 paths, the delta r, but then you also have the half wavelength phase shift, so was this constructive or destructive at that point? If you do anything with just generalized interference, it would involve something like that, as opposed to like the thin films or whatever. But generally, the interference type problems are going to involve diffraction. You're going different paths from the different openings. And is that the integer of a wavelength or a half integer of a wavelength?
On the polarization, does it say theta 1 equals theta p?
Theta sub p.
Yeah,
If
okay.
this is 100% polarized, then this theta 1 is called the polarizing angle.
Okay. I was just making sure it said theta 1 equals theta p.
Yeah. Of course, this is reflection here, so this is also theta 1.
Mm-hmm.
But this incident angle in your Snell's law then becomes the polarizing angle if this reflected ray is 100% polarized, which means then the reflected ray and the refracted ray are at 90 degrees to each other. Well, it might be saying something like, what's the polarizing angle if you got these two indexes? Or if you got, or you might have, you got air, so N1 and your N2 is, well, maybe you don't know N2. But you're told that the theta 1 is, say, 40 degrees, and theta 2 is 27 degrees. And so what is the polarizing angle? Well, knowing this and this and this, I can find theta 2 by using Snell's law. I've got 1 times sine of 40 is equal to N2 times sine of 27. So the N2 is the sine of 40 divided by the sine of 27, which gives you 1.416 approximately. And therefore the polarizing angle, and take this, go to this equation, say that tangent of the polarizing angle is the 1.416 divided by 1. And so the arctangent of that polarizing, or that index is now 54 rounded off 0.8 degrees. So yeah, it's asking for the polarizing angle. Well, that's that tangent is equal to the N2 over the N1. But I need to know what the N2 is. And just because I gave you 40 and 27, that doesn't mean the 40 is the polarizing angle. It says when you do refraction, here's theta 1, here's theta 2. Using Snell's law, find N2, and then knowing N2 and N1, find the polarizing angle. Or it might say the polarizing angle is whatever, 60 degrees. So if you're going from air to this other material, and the angle in air is the 40, what's the angle in the other material? So I could use this to find the N2, and then knowing N2 and N1 and the theta 1, you go back to Snell's law to find the theta 2. You involve both Snell's law and the tangent of theta is N2 over N1 equation. Otherwise, it's so simple that it's hard to say, that's going to be much of a problem there. But anyway, so, do you have any other questions on this? What? No. I won't give you problem involved with this. There'll definitely be something involving Snell's law. I'll guarantee you that. There'll be something involving mirror and lenses. Probably a double lens. There can be three problems out of these equations. Single mirror, single lens, double lens. There'll be a diffraction problem, for sure. Something. There'll probably be a polarization problem. There'll probably be a resolution problem. And may or may not have something involving this halfway point phase shift on reflection. There's at least 7 problems, individual problems right there. And again, there's a total of 10, so 3 more with, so some of these are gonna have double type problems. I gave one problem one time. I think it was on a final, where I had it was like a lens. It had the P's moving toward the lens at some speed. And the question was how fast, when the lens is a certain distance from or the object is a certain distance from the lens, how fast is the image moving? So if P is moving at a certain speed, and when P is at a particular distance, how fast, what's the speed of the cube? Instead of being just stationary, they're moving at that point. Well, the speed of P is just like dB dt, right? V is dx dt. So the speed of this would be a dP dt. But then, how is dB dt related to dq dt? Focal length's constant, it's not changing as you move the object. So could you take the derivative of dq dt with respect to dp dt? One way to do it, just solve that for q in terms of p, and then take the derivative of both sides. And then there's this sledge was telling me one time, oh, you just do this to it. She called it implicit differentiation. Which does make it quicker to do the differentiation, but you can still do it the other way. They're equivalent to each other. They don't look like it when you first do it, but it is equivalent. So yeah, you could get into something where you've got a derivative going on there, but okay, I won't give you anything involving a derivative for this test.
So we're not gonna have that kind of question on the test, but it might be on the final.
Oh, it's good thing. Since I told you about it, well, I probably shouldn't give it to you. Right? Anyway, that's something very made up because nothing in all of these equations involve time. Like we have magnetism and electricity, and therefore it makes it harder to come up with something that involves calculus. Anyway, yeah, just, if you can, main thing there, okay, what kind of problem is it to start with? Is it just refraction? Is it mirrors? Is it lenses? If it's lenses, is it one lens or two lenses? Is it diffraction? It talks about spacing between two openings, or it talks about a grating with so many numbers of openings. Maybe you're looking for how far away is it? You're looking for the y value. Or you're looking for this angle. Or you're looking for the distance between. Or maybe you're looking for how many openings do you have per unit length. If you find the d from this equation, then you can do the n. But something involving a grating at that point. Is it polarization? got this equation, maybe Snell's law also, but you definitely have that equation if it's a polarization problem. Is it resolution? Talks anything about how far apart two things are, or how far away they are, or what's the diameter of the thing that you're looking through. Well, then I've got a resolution problem. I've got these two equations that are at least applicable. Main thing on this, it looks sort of like a triangle here. Don't do anything with sine, cosine, or tangent. The angle is in radians, here and here, but don't try to get into doing sine, cosine, or tangent, because you're probably going to mess something up, and it's not going to be the right answer. Plus, technically, these are not right angles. Either one of those, they would be. It's an isosceles triangle, and no, they're not right angles there. But that would be resolution. So figure out what kind of problem it is. That limits which equations you've got to work with. And then how can you use those equations to figure out with what you're given, what you're looking for. That's going to be the whole process and all that. Any other questions?
We're going to talk about light mixing.
Yeah. Saw a good article about that. Reading it Monday. This magazine that was talking about ways to teach various things. It was one of the articles was on colors of light, about light mixing and stuff, additive mixing or subtractive mixing. What I was doing with y'all was additive. Put the red and the blue together, you end up with the magenta. The blue and the green, you get cyan. Or the green and the red, you get yellow. That's additive, adding the colors together. Anyway. So no, nothing on color mixing.